When we consider a first-order reaction, or more specifically one that is first order with respect to a particular reactant, we can describe the rate as the change of that concentration over time. And that's a derivative, right? We have a change happening. We have a rate. Rates are always derivatives. And like any derivative, we can in fact integrate it. And in doing so, we'll actually get some very useful formulas out. Thankfully, we do not need to do the calculus. The magic of copy-paste will save us. If this is integrated, you get the following, that the natural log of the concentration at time point t minus the natural log of the concentration initially will be equal to negative kt. Although we very well typically will rearrange this equation to say that the natural log of concentration A at time t is equal to negative kt plus the natural log of our initial concentration. And this means that we can use this to figure out the concentration of a particular reactant or product at a given time. We can use this to determine there we go, at whatever time we want, once we know the constant. And very importantly as well, we see that we can do this because this is a linear formula. Essentially, we're saying that y, or f of x, here I'll put it in purple, f of x, or y, whichever way you want to think about it, is equal to mx plus b. Right? Our b is a constant, that's our initial, the natural log of our initial concentration. Our y value, or f of x as we might call it, here we can put y in if that makes it a little bit easier, would be our natural log. So we can solve for y. Solve for the natural log of our concentration at a given time. And if we do so, we see that we have a slope and our time constant, which is our x value here. So when we're looking at a graph of this, our rate constant is in fact just the negative slope. So that's something to note here. That for a first order reaction, we might see that time and concentration follow the kind of exponential thing we looked at earlier. But we see that if we plot instead the natural log of the concentration, we should get a linear plot. And so this is very valuable because that means we can say, aha, if we know what we started with, aka our y-intercept, that's the amount we started with, that's b, right? That's our initial concentration of A. We can figure it out. Say if we want this point, we can figure it out. We can say, I want to see what's going to happen at 1 minute. How much reactant do I have left? That's what this value is for. And this, of course, is for first order reactants, or products, you could say. So remember that reactions can be first order with respect to a particular reactant, or they can be first order overall. This is for first order with respect to a particular reactant. Let's take a look at this. I have got some values for us here. We have product, or A turning into B, our favorite reaction. I've got the data. We'll say this is at 510 degrees Celsius, because why not? This is a first order process with a rate constant times 10 to the negative 4 inverse seconds. That's our rate constant. We have the following. If our initial pressure, remember that pressure and concentration are interchangeable here, is 135 torr. Or if we really wanted, we could figure out the concentration by using the ideal gas law, but let's not worry about that. We can just use the pressure directly. What is the pressure at 1420 seconds? So if our initial pressure is 135 torr, we can figure out the pressure at 1420 seconds by using our integrated rate law. So this is something you'll probably watch to learn, right? This formula, negative kT times, plus the natural log of concentration at time 0. Again, pressure and concentration for a gas are interchangeable because they are related to the ideal gas law. So if we want to go ahead and do this, we can see that we can just plug stuff in. We can solve for the natural log of our concentration, which we can then solve using mathematics, right? So if we're looking for this, we can plug in what we know. We have negative 6.8 times 10 to the negative 4. We have 1420. Notice that we had seconds and inverse seconds. Those cancel out, which is what we should see. Plus, we have the natural log of 135. Again, we can use torr here. Any pressure unit's fine. We'll just get the same pressure unit at the end. So, we simply need to figure this out. So, calculator. So if we go ahead and solve all this mathematics, we have negative 6.8 times 10 to the negative 4 times 1420 plus the natural log, where's my natural log button? There it is, of 135. We get that the natural log of a sub t, say a sub 1420, I suppose, is 3.9396, blah, blah, blah. And so that means that a at our time interval of interest would be e to the 3.9396. Remember, that's how natural logs work. In order to get rid of a natural log, you have to use the exponent function. And so on your calculator, you see I've got our values here. We want to do e to our answer, like thusly. Doing so, we get our answer, which is going to be that our pressure of whatever this compound is, A, should be 51.4 torr. Our units stay the same as they were before. Natural log gets rid of units, but you should have the same unit you started with. Remember that, again, I'm going to note this, although we have been focusing on concentration, pressure and concentration are interchangeable for gases. As long as you're using the same thing throughout. Don't start with one concentration and then use a pressure later. Use pressure for both. Pressure and concentration are equally used here for gases. Obviously, we're not going to use an osmotic pressure or something. I suppose we could, but it'd be bizarre. For gases, we can use either pressure or concentration. So molar, or we can use pressure. Torr, atmosphere, wherever it may be. And again, it's just going to be the same unit that we have before. So once you solve mathematically, remember the only thing special here is that we have to use e to the x to figure out our actual values here. All right, so again, I've kind of used concentration here as our formula just to keep consistency, but remember that pressure and concentration are interchangeable for each other when we are using the same thing in the same problem. And so the last thing I want to point out again is that you can determine whether a particular reaction is first order by looking at the graphs. We see that a graph of concentration versus time is exponential. That's the case for first order and second order. However, if we plot the natural log of concentration over time, then we see that we have a linear relationship. If you see a linear graph, that means that your reaction is first order in respect to that reactant. So this reaction, because that's a straight line for ln A over time, we are going to say that this reaction is first order with respect to A. And so we may see that Excel is a very useful tool for us, or Google Sheets, something similar where you can put in data points and graph it. So you can figure out, you can take your concentration, plot that versus time. You can take the natural log of all your concentrations, plot those versus time. And as we'll see for a second order, you have the inverse, which we'll see in our next video.